So, welcome to this class on hardware security. So, today we shall be continuing on our discussions on fault attacks. In particular, we shall be talking about multi-byte fault attacks and also like fault attacks as targeted on the key scheduling. Like previously we have seen like fault attacks on AES where the data path was targeted. So, here we will see how to exploit a fault analysis where the target is the key schedule of AES. So, therefore, we shall be talking about two types of fault attacks. The first one is called as diagonal fault attacks and the second one is where we target the key schedule of AES. To start with, we have basically been considering what are called as single byte fault attacks. So, we have been considering the fault essentially where the fault is restricted to a single byte of the state matrix of AES. But here we will be considering the fact that suppose like when you are trying to induce the fault propagates to more than 1 bytes. And it basically kind of touches pretty much upon like 2 bytes or 3 bytes or more than 1 bytes in general. So, of course, the fault value should be a non-zero value, but it can be any arbitrary value. Okay. So, what is the advantage of doing a fault analysis based on that? So, it basically improves the fault coverage, because as we know that when we are trying to induce a fault and if we can develop a fault attack strategy which can encompass or which can exploit all possible types of faults, right, essentially then we have got more and more coverage. So, of course, as we will see that we are not able to get 100% fault coverage, but nonetheless, right, we will try to extend the fault coverage of our existing fault analysis. Okay. So, in this pursuit, right, let us again take a quick recap on the AES algorithm. So, you have got, this we are talking without loss of generality with respect to AES 128. So, we know that there are 9 rounds of the AES algorithm which has got these blocks like the add round key, the sub bytes, the shift rows, mixed columns and add round key. And then there is the final round which essentially has everything but not the mixed column. So, there is the mixed columns which is kind of removed from the final round. So, now we will be defining the fault model in this case. So, it is essentially what is called as the diagonals of the AES state matrix. Okay. So, what we will try to do here is consider the AES state matrix and then define certain diagonals in this context. Okay. So, therefore, right, imagine that suppose essentially these bytes, for example, this is the state matrix of AES and consider these diagonal like B00, B11, B22 and B33. So, this forms my diagonal D0. Okay. On the other hand, consider these bytes like B01, B12, B23 and along with it consider B30. Okay. So, these together forms what is called as a diagonal D1. Okay. Likewise, consider this diagonal like this and this. Okay. So, these two makes what is called as a diagonal D2. Okay. And likewise, consider this byte, that is B03 and B10, B21 and B32. So, this forms my diagonal D3. Okay. So, these are the 4 diagonals as stated over here D0, D1, D2 and D3. Okay. So, now we will basically try to like define a fault attack on AES based on these definitions of diagonals. So, we have till now, right, we have been talking about the fault model where the fault model was a random byte, but now we will be trying to extend that fault model into what are called as diagonal fault models using these 4 definitions or 4 diagonals in the AES state matrix. Okay. So, now let us see how this works. So, therefore, right, I mean we would like to kind of we can of course like in typically write because of the regular structure of AES, we can define the diagonal DI in this compact form where DI is basically given by the bytes Bj and Bj plus I where I and then modulo 4 in the index and we vary j from 0 to 4. So, you can easily see that if I plug in say I equal to 0, okay, then that means like I am considering the bytes like B, say B0, j plus I, that would be like B0 comma 0. Okay. If I plug in the value of j equal to 1 here, okay, so that means like I am considering B1 comma 1, okay, and likewise B2 comma 2 and B3 comma 3. Okay. Likewise, I can define for D1, D2 and D3. Okay. So, this is the general and compact form of representing the diagonal. So, therefore, right, I mean with this definition, let us define the fault for 4 fault models. Okay. So the first model is what we call as where one diagonal is affected. So you see that in this particular diagonal or in this particular model, when we are talking about the M0 essentially as one of the fault models, then only one diagonal is affected. Okay, that means, like, remember the 4 diagonals, so it may be that the fault is, as you can see here, is restricted to the diagonal D0. Okay. So likewise, right, we could have scenario where the fault propagates to 2 diagonals. Okay. So if there are 2 diagonals, this is essentially what we have. So you can see that here diagonal D0 is affected, and also, right, we have got this diagonal which is affected. Okay. Remember that these 3 bytes and this byte are in the same diagonal. Okay. So likewise, you have model M3 or M2 where there are 3 diagonals which are corrupted, and in model M3 pretty much any of the 4 diagonals are corrupted. Okay. So you can easily see that model M3 is like universal, because all possible faults in the AES state matrix would imply model 3, because I am saying that all the 4 diagonals can also be corrupted. Also at the same time, you can see that these models subsume each other, which means like M0, right, essentially is kind of a subpart of M1. Because if I am saying that the fault is in one diagonal, that means like it is within the fault model pertaining to model M1. Okay. Because in model M1 I am allowing 2 diagonals to be corrupted. Okay, and it may happen that out of these 2 diagonals only one diagonal is corrupted. So we can say that M0 is a subset of M1, which is a subset of M2, which is a subset of M3. Okay. So therefore, right, we have got these 4 fault models, and now, right, we will try to see that whether we can exploit these possible fault models. So again, this is our fault injection setup. Again, it's kind of similar to what we have done previously. So we have got the AES iterative hardware implemented, and we are again kind of tinkering with the clock line. Okay, so we can again try to induce the fault in other mechanisms, but consider that this is a simple and cost effective way of experimenting on the fault injection, where we basically try to change the clock frequency suddenly, say when the clock when the 8th round starts or initiates, then we switch from a slow clock, that means a clock at which AES is operating correctly, to suddenly a fast clock, and this sudden switch, right, creates internal faults which are observed as the required faults. Okay. So what we do is that these faults are basically observed by an embedded logic analyzer. So this is implemented using a Xilinx ChipScope Pro embedded logic analyzer to inspect like how the internal faults behave. Okay. So for injecting the like the sudden clock frequency, we have used an arbitrary function generator, and essentially, right, this is pretty much the implementation setup that we have. So now, right, with this setup, we are now set to kind of understand how the fault propagates. Okay. So in particular, observe, right, that we are basically considering faults where the fault is according to the fault model M0 in this case. Okay. So what does it mean? That means like only one diagonal is corrupted. Okay. So we know that there are 4 diagonals, so the fault could be either in D0, or it could be either in D1, or it could be in either in D2, or it could be either in D3. So it could be any one but not 2 diagonals. Okay, that's the whole idea. And if you consider here, for example, if you consider this state matrix, you will see that only 1 byte in diagonal D0 is corrupted. If you consider this particular, like you will see that 2 bytes are corrupted. Likewise, you see that the fault propagates to 3 bytes and finally 4 bytes, but all of them ensure that the fault is restricted to one diagonal, and in fact this is diagonal D0. So now let us see, right, and we have already kind of seen, right, how to do a fault attack when the fault is of this type, but the interesting thing that we will see is now is that even these kind of faults are also similarly exploitable. Okay. So remember that the fault location is at the input of the 8th round, and because of that, right, if you observe the fault propagation, you will see that this is what will happen is after the bytes are. Okay. So here there is 1 byte, so 1 byte gets corrupted here. Here there are 2 bytes, so therefore the fault kind of spreads to 2 bytes and makes an like a bijective transformation. Here the fault is in 3 bytes, so therefore we get a mapping in 3 bytes. Here there are 4 bytes, and therefore we get a mapping in 4 bytes. Okay. And then this is followed by the shift row, and in the shift row we know that in the first row there is nothing which happens, but in the second row, third row, and the second, third, and the final one, in all of them what happens is that the first column, right, is kind of getting disturbed. So you see that the disturbance in all of them is restricted to the first diagonal. Okay, so the first column at the input of the first diagonal, or one diagonal at the input of the 8th round, is basically transformed into one column, right, at the end of the 8th round. This is a property of the AES transformation. Now because of this, right, when the mixed column comes in, right, at this point, then we know that all the, because of the mixed column property, right, the mixed columns has a specific property, and because of that property we know, right, that at this point what we obtain is that we basically see that we get a disturbance, right, which is of this type. Okay. And now what happens is that after byte sub we have got the fault which propagates, which kind of is like F1, F2 and F3 and F4, right, and therefore what happens, right, after shift row, that means after the 9th round shift row, these bytes gets kind of distributed into 4 columns of the AES state matrix. Okay. And that implies that after mixed columns, okay, after the mixed columns operation, right, what happens is that this F1 gets transformed into these equations, that is 2F1, F1, F1 and 3F1, and likewise you have got F4, F4, 3F4 and 2F4 and so on for F3 and also for F2. Okay. So this is because of the mixed columns which takes place at this point. Okay. But the interesting take home at here is that for all these faults that we have, that means the faults, as long as the fault is restricted to the diagonal D0, the equations here remains an invariant. Okay, it doesn't change, which means all these faults fall into the same equivalence class and they are equivalent. Okay, so the faults induced in diagonal D0 at the input of 8th round are therefore all equivalent. So this is an important and interesting observation that we observe here. So as you can understand that now we can essentially kind of like reduce the possible key size in a similar way. We will basically work behind as we have done previously, and we will be trying to exploit these equations as we have done previously. Okay. And if you remember, right, previously what we have done is that for at least for this case, for a single byte fault, we have seen that a 2 power of 128 AES key because of one such fault gets reduced to 2 power of 32 possible values. Okay. So this reduction is possible even now, even if the fault propagates to more than 1 bytes, but is restricted to one diagonal. Okay. In fact, you do not know which of the diagonals get, or you may not know like which of the diagonals get corrupted, and you can make a guess, right? You can make a guess that there are 4 diagonals, and if you are told that the fault propagates according to the model M0, you can basically guess which of the diagonals has got corrupted. Okay. And if you guess that, then that would imply that you basically have got either of these 4 situations. The fault has either happened because of D0 or D1 or D2 or D3, and depending upon that, right, you have got 4 sets of equations. Okay. So therefore, right, you have to basically kind of guess either of these things, and you have to basically kind of solve for any of these equations. And that actually means that you can actually reduce the AES possible key size to so in this case, right, you can again take the ciphertext, and here it is shown that suppose the diagonal D0 is affected, and this is your ciphertext and this is your faulty ciphertext, and this is your corresponding 10th round key. So what you do is that you basically kind of reverts back and target the quartets and kind of try to solve each of these quartets using or solving a similar kind of equation as we have previously seen. Okay. So if you remember, right, previously we basically exploited the fact that these differentials are like twice this, and this is the same as this one, and this is the thrice as this one. So we kind of form similar set of equations, and this is exactly like this is twice this one, this is equal to this one, and this is thrice this one, and we basically solve them. Okay. So therefore we know that there are in total 4 such system of equations for the diagonal D0. And so in general, right, you would expect that the AES key size would get reduced to around 2 power of 32 values. And right, if you know that there are 4 possible diagonals which can get corrupted, then that would mean that even if you allow that I do not know which is the exact diagonal, then that would mean that the key size would be 4 multiplied by 2 power of 32, which is essentially 2 power of 34. Okay. So now you may wonder that what happens, right, if the fault kind of propagates to more than 1 diagonals. Okay. So this is the scenario that we will basically cover next. So remember that in the previous case, right, if you want to kind of do the attack, then the attack essentially has got because you are reducing the key size to 2 power of 32 values. Okay. So in this case also, right, you will see that there is an information theoretic reduction of entropy. For example, right, we are considering now faults which are propagating according to 2 diagonals. So that means, right, either say so in this case I have shown for diagonal D0 and say diagonal D1. So you can see that there are 2 diagonals which are corrupted. Okay. So that could happen, right. You have scenarios like this where maybe even 8 bytes out of 16 bytes are corrupted by faults. Okay. So for each of them, right, therefore if there are 2 diagonals which are corrupted at the input of, or 2 diagonals which are corrupted at the input of the 8th round, that implies that there are 2 columns which are affected at this point. Okay. Again, because of the mixed columns, right, because of the after shift rows, you will have a situation like this, where you can see that the 2 diagonals here or the 2 columns here are kind of spread across in the state matrix. Okay. In the first row, right, there is no shift here. In the second row, there is a circular left shift. So therefore, this F6 comes here as F2, okay, and F2 comes here as here. So likewise in F3 and F7, right, they all get propagated in this fashion. So what is the property here? So the property here is that per column, right, per column there are at max 2 disturbances. Right, there are at max 2 disturbances, or 2 bytes, there are at max 2 byte disturbances. So therefore now if I apply the mixed columns, I get something like this. I get 2f1 plus 3f6, f1 plus 2f6, f1 plus f6 and 3f1 plus f6. Okay. So that implies that in the unlike the previous case, and actually somewhat similar to the previous case, so you see that there is a similarity and there is a dissimilarity. Okay. So what is the similarity? In the similarity, right, is this, that in the previous case the column had an 8 bit of entropy because there was only 1 byte or 1 independent variable. If you guess that, right, then the remaining column gets fixed. Okay. In this, right, you have got 2 bytes which are independent. For example, f1 and f6 are independent. The moment you guess f1 and f6, this particular column gets fixed. Okay. So that means there is 16 bits of entropy. Okay. And therefore, right, you will see that what you can do is you can now set variables like in the previous case, like I said, a0, a1, a2 and a3 to all these 3 values, or all these 4 values, like 2f1 plus 3f6, f1 plus 2f6 and f1 plus f6, 3f1 plus f6. These are all differential equations, and you can actually eliminate like f1 and f6 because there are 4 equations now. Okay. And there are 2 variables, right. So therefore you can eliminate them and you form 2 equations, and as you can see, right, this equation is in terms of a1, a3, and on the right you have got a0 and a2. Okay. So therefore now what you can basically do is that you can take these equations, and using these equations you can try to solve the ES key. Okay. Again, as you observe that because of this reduction in entropy of this column, you can reduce the possible entropy of the ES key. Okay. So what does that lead to? So you can observe here that in a similar, or doing a similar analysis, you can write equations as if this form, like a0, a1, a2 and a3. These are again the inverse sub byte when you are again going back. So you basically essentially come to this column. So that is a0, a1, a2 and a3, and that is written over here. Okay. As previously, right, therefore you can now relate this a0, a1, a2 and a3 by these 2 equations, and that would imply that you have got what you are basically doing is you are reducing the AES key size to now 2 power of 16. So there are 4 key bytes involved here, and because of this entropy reduction, that gets converted into or reduced to 2 power of 16 values because you have 16 bits of entropy. Okay. So therefore, right, you basically reduce it to 2 power of 16 values, but then there are 4 key quartets. So that means that the total key size now diminishes to 2 power of 64. Okay. So if you compare this with the previous case, like when you had got only 1 diagonal affected, and like which diagonal, then the total key size is reduced to 2 power of 32. But here when you have got 2 diagonals corrupted, then the key size reduces to 2 power of 64. Okay. So again, like if you get 2 such faulty ciphertext, then you can again intersect them and you can pretty much reduce it to a unique value. Okay. So the idea is that but at the same time you have to keep in mind that you have to you have to basically observe like 2 power of 64 values and then take a possible intersection, okay, which may not be very practical. Okay. On the other hand, when the fault is kind of restricted to a one single diagram, then the attack is more practical because you are essentially able to operate with 2 power of 32 values quite easily. Okay. But on the other hand, right, this also shows that theoretically there is a leakage, okay, and that is something that is not very comfortable from the designer point of view. So likewise, what happens when the fault propagates to 3 diagonals? So here is a fault model M2, and as you can see, right, now we are considering scenarios where there are like 3 diagonals which are getting corrupted, and it can therefore like lead to a scenario like this where you can see that 12 bytes out of 16 bytes are corrupted. Okay. Again, if there are 3 diagonals which are corrupted, then that means that here you have got like here you have got all the three columns which are corrupted. And here it means like that every column, if you see, right, because of the shift row, there are at most 3 bytes which are corrupted. Okay, so like previously, right, here at most 3 bytes are corrupted. Okay, so now if we apply mixed columns, so again you will get some relationships, like as you can see among these 4 bytes. And as you can observe, now there are 3 independent bytes, okay, and that would imply that now you have got like 3 individual bytes which are of of consequence, and therefore, right, the entropy is now like 3 into 8, that is essentially 24 bits, okay, per key quartet. Okay, so if you observe, for example, this column here, then this column has got an entropy of 24 bits. And that you can easily see that if I write each of these values like as A0, A1, A2 and A3, and then I can solve, right, I basically get only one single equation. Okay, and essentially, right, this equation getting satisfied, there is a probability of 1 by 2 power of 8. Okay, and another way of seeing this is that, okay, the probability of a random selection of A0, A1, A2 and A3 satisfying this equation is 1 by 2 to the power of 8. And I know that totally there are 2 power of 32 values, so I get 2 power of 24. Okay, so this is another way of looking at it. So now, right, I mean, so therefore, right, what is the implication of this on the key size? So again, you can form similar equations as previously, similar differential equations by writing each of these column values as A0, A1, A2 and A3, and then kind of solving them as we have seen, right. We know that A0, A1, A2 and A3 are kind of dependent. So what I do is basically I guess these key values K1, K8, K11 and K14 is guessed here, and then we try to see that whether they satisfy this equation. Okay, as you can see, right, that out of 2 power of 32 values in this case, right, because of this relationship, there will be 2 power of 24 values which will satisfy this equation. Okay, so what you can probably do is that you can take 2 power of 24 values, okay, and right, you can actually like try multiple attempts. Okay, so what you can do is that you can kind of intersect them and you can reduce the possible key size. Okay, so for example, here what I can do is that I can take 4 faulty ciphertext and I can like try to kind of intersect them, and apparently in that case, right, I get a unique value for this key quartet. Okay, but at the same time, right, with a single fault injection, right, it would imply that I have got 2 power of 24 whole to the power of 4, that is 2 power of 96 as my key size, which is kind of quite big, but at the same time it is less than 2 power of 120. So it is theoretically it's an attack, but at the same time, right, it may not be very practical with a single fault injection. Okay, so on the other hand, what you can do is that you can reduce each of the key quartets by trying multiple attempts, right, and recovering each of the key quartets individually. Okay, so let us see what happens, or what is the impact of this finding on an experimental basis. So again, like if you remember, this is my like basic setup, and imagine that the AES operates at 36 megahertz. Okay, so what we do is that we tried 512 fault injections by using the clock generator. Why 512? Because that is the limit of the embedded logic analyzer. Okay, so we then take a statistical analysis of how the faults distribute across the models M0, M1, M2 and M3. Okay, so what we observe that initially when the clock is operating at its correct frequency range like 36 megahertz or maybe slightly around that, there are no faults. Okay, and that's why, right, we get M0, M1, M2, M3, all of them having 0 values. That means there are no faults which are going into these pockets. At the same time, there are 512 cases where there are no faults. That means all of them are resulting in no faults. When I am trying to increase the clock frequency, for example, I make it say 36.3 megahertz, I start to get the first signs of faults. As you can see, the number of no faults is now reduced to 510, and I get 2 faults which follow or belong to the model M0. That means I get faults where where the fault is restricted to one diagonal. Okay, it may be in 2 bytes, but the fault is is not going across diagonals. Okay. On the other hand, when I start increasing the clock frequency, what I observe is that I get faults also in the M1 category, which means like there are more than 1 diagonals which are now getting corrupted. Okay, And likewise, when I start to increase the clock frequency further, I have situations where the fault propagates according to model M2, and also when I increase it further, I get all the 4 diagonals which are corrupted. That means the faults are now according to the model M3. Okay. So as we have seen, right, as a finding or as a result of this discussion that we had, now you can actually exploit till this point where you can see that the faults are not according to the model M3. Okay, as long as a fault is restricted to the model M2, that means 3 diagonals out of 4 diagonals are corrupted, albeit with with more fault injections, we can still try to kind of reduce the AES key size. Okay, and in fact, right, we can do the attack pretty much with one single fault, even right when the fault is restricted to only one diagonal. That means when I am still operating at a region where the M0 faults are dominating. Okay. So therefore, right, and the interesting thing is that this particular characterization can be done per device, and it seems like that even if you want to kind of shut down and again restart the machine, right, you again get a similar kind of characteristic. Okay, so you can basically study a platform, and based upon that you can try to find out what should be your ideal clock frequency selection, so that you get faults where maybe the faults are in this case, right, are according to model M0 with more probability. Okay. But at the same time, right, even if the fault propagates to more than 1 bytes, but as long as it kind of is restricted into one single diagonal, you can still apply these techniques. Okay. So basically, right, I mean, at this point we are kind of done where we have seen how to kind of target the fault, like the fault, where the fault targets the AES data path. What we will see next is that what happens, like where the faults target the key schedule of a block cipher. Okay, so therefore, we have been targeting only the data path now, but we will now investigate on what happens, right, when the fault is kind of touching on the key schedule of AES. Okay, but that we will take up in the next class. Thank you.